There is a gap between what we dream and what the universe actually permits. Mars sits there in the night sky, a faint reddish point of light, close enough to see with the naked eye on a clear evening. And yet the distance between our planet and that one is not merely a matter of miles or kilometers. It is a matter of physics, biology, and the cold, indifferent arithmetic of the cosmos. When we talk about sending human beings to Mars, we are not talking about a long flight. We are talking about a sustained collision between the ambitions of a fragile biological organism and the hard, unforgiving laws that govern how matter and energy behave across the void of space. And when you examine those laws carefully, the picture that emerges is not one of challenge to be overcome. It is one of fundamental, perhaps permanent impossibility. Let me take you through the numbers first, because the numbers tell a story that our intuitions are almost perfectly designed to misread. At its closest approach, Mars is about 54 million kilometers from Earth. That sounds like a lot, but the human mind evolved to think in terms of savanna distances, of village-to-village travel, of coastlines crossed in weeks. So 54 million kilometers lands in our brain with about as much emotional weight as 54,000. It does not. The fastest spacecraft ever launched from Earth, Voyager 1, reached speeds of around 17 kilometers per second. At that speed, a straight-line trip to Mars at its closest would take roughly 39 days. But spacecraft do not travel in straight lines through the solar system. They follow curved orbital paths dictated by gravity. The most fuel-efficient path, the Hohmann transfer orbit, takes between 6 and 9 months. That is the journey. 6 to 9 months of travel each way in a tin can hurtling through a vacuum. Now here is where the physics becomes personal. The human body did not evolve in a vacuum. It evolved on the surface of a planet with a specific gravitational pull, a specific atmospheric pressure, a specific magnetic field shielding it from radiation, and a specific biological ecosystem of microbes that it has spent millions of years co-evolving with. Remove any one of these, and the body begins to fail. Remove all of them simultaneously, as you must when you send a person into space, and you are putting a biological system under a kind of stress it was never designed to handle. Start with gravity. In microgravity, bone loses density at a rate of roughly 1 to 2% per month. The muscles that support the skeleton begin to atrophy. The fluid distribution in the body shifts. Blood pressure regulation changes. The optic nerve swells, and in a significant fraction of astronauts, this swelling causes lasting changes to vision. These are not minor inconveniences. After 6 months aboard the International Space Station, returning astronauts can barely walk. They have to be carried out of the capsule. They spend months in rehabilitation before they recover something approaching normal function. Now ask yourself, what happens to a crew that spends 9 months in microgravity traveling to Mars, lands on a planet with only 38% of Earth's gravity, spends time on the surface, and then has to make the 9-month return journey? They would be arriving on Mars already significantly degraded. They would spend their surface time continuing to degrade. The return journey would be a 9-month medical emergency aboard a vehicle with no emergency services available. This is not a problem we can solve with better exercise equipment, though exercise helps at the margins. The fundamental issue is that the human skeleton is a weight-bearing structure that requires weight to maintain itself. It is a feedback system calibrated to Earth's gravitational field. You can slow the deterioration, but you cannot stop it. Not with the technologies we currently possess, and not with any technology that exists even on the theoretical horizon. Radiation is the second wall. Earth's magnetic field acts as a planetary shield, deflecting the constant barrage of high-energy particles streaming from the sun and from distant supernovae across the galaxy. Astronauts in low Earth orbit, like those aboard the International Space Station, are still within the outer edges of that magnetic shield. They receive elevated doses of radiation compared to people on the ground, but the shield provides meaningful protection. Beyond low Earth orbit, beyond the magnetosphere, there is no shield. There is nothing between the human body and the full, unfiltered radiation environment of interplanetary space. The radiation comes in two main forms: solar energetic particles, which are bursts of high-energy protons and heavier ions thrown off by solar flares, can deliver a life-threatening dose in a matter of hours. Galactic cosmic rays, which are high-energy particles accelerated by distant astrophysical events, arrive in a steady, low-level stream that is extremely difficult to shield against because the particles are so energetic that thick shielding materials actually generate secondary radiation cascades when struck. Water and polyethylene are among the best shielding materials we know, and you would need meters of it to provide meaningful protection against galactic cosmic rays. Meters of shielding on a spacecraft adds thousands of tons of mass, and mass is the one thing in spaceflight that is most brutally expensive. The fuel required to accelerate mass increases exponentially with the mass itself. NASA's estimates for a Mars mission suggest that crew members would receive radiation doses in the range of 1 sievert over the course of the round trip. The current career limit for an astronaut is around 1 sievert. A Mars mission would essentially consume a person's entire lifetime radiation budget in a single round trip, and the associated cancer risk would be substantial. Models suggest a meaningful increase in lifetime cancer mortality for every person sent on such a mission. That is not a problem of engineering. That is a problem of physics. The radiation exists. The particles are real. The damage they do to DNA is well understood. You cannot negotiate with ionizing radiation. But suppose for a moment that we could solve the radiation problem and the bone density problem and the muscular atrophy problem. Suppose we had some technology, some pharmaceutical or mechanical intervention that kept the body whole through the journey. There is still the question of the return, and this is where the physics of the mission becomes what engineers sometimes call the tyranny of the rocket equation. The rocket equation, derived by Konstantin Tsiolkovsky in 1903, describes a brutal mathematical relationship. To accelerate a given mass to a given velocity, you need propellant. But that propellant itself has mass, which means you need more propellant to accelerate the propellant. And that additional propellant has mass, requiring still more propellant. The equation is exponential. It means that for any given mission, the ratio of propellant mass to payload mass grows very rapidly as the distance and velocity requirements increase. For a Mars mission, this is catastrophic. The fuel required to send humans to Mars and bring them back would dwarf the mass of the spacecraft itself by an enormous factor. The solution people propose is in situ resource utilization, which is the idea of manufacturing rocket fuel on Mars using the Martian atmosphere and soil. Mars has carbon dioxide in its atmosphere and potentially water ice in its subsurface. In principle, you could use these to manufacture methane and liquid oxygen, which are the propellants SpaceX's Raptor engines burn. This is technically feasible in a laboratory. Scaling it to the level required to fuel a Mars return vehicle using equipment that had to survive a 9-month transit, a landing, and an extended stay on a planet with extreme temperature swings, dust storms that can engulf the entire planet for months at a time, and no repair infrastructure is an entirely different proposition. The dust storms alone deserve attention. Mars experiences planet-wide dust storms that can last for months. During these events, sunlight reaching the surface drops dramatically. Solar panels, which would be the primary power source for any early Mars base, can lose 80 to 90% of their efficiency. The Opportunity rover, a robotic vehicle with no life support requirements, died in a Martian dust storm because it could not generate enough power to keep itself warm. A human crew dependent on solar power for life support, heating, and propellant production would face an existential threat every time such a storm developed. Dust storms cannot be predicted months in advance with our current understanding of Martian meteorology. A crew could find themselves in a race against a global dust storm with a partially completed propellant load and a narrowing launch window. That launch window matters enormously. Earth and Mars align for optimal transit only every 26 months when they reach a configuration called opposition. Miss that window, and the next departure opportunity adds years to the crew's stay on Mars. A crew stranded on Mars waiting for the next launch window would need enough food, water, power, and breathable air for that entire extended period. The logistics of that resupply, the mass of consumables required, fed back through the rocket equation, makes the numbers even more extreme. Let me add one more layer to this, because the physics of the situation becomes even more unforgiving when you consider the communication delay. The speed of light, which is the absolute upper limit of how fast any signal can travel, means that a message from Mars takes between 3 and 22 minutes to reach Earth, depending on where the two planets are in their orbits. At maximum separation, a question and its answer take nearly 44 minutes to complete their round trip. There is no real-time communication. There is no mission control intervention in any emergency that unfolds on a time scale of less than an hour. The crew is on their own in a way that no crew in the history of human spaceflight has ever been. Every decision, every medical emergency, every technical failure must be handled by people who are already physically compromised by months of microgravity and radiation exposure, operating complex life support and propellant production equipment on an alien surface in suits that must be maintained without spare parts, in a habitat that must function without failure for years. The probability of mission success, defined not just as reaching Mars, but as returning all crew members alive under these constraints, is not something that can be driven to acceptable levels by training and redundancy. The failure modes are too numerous, too independent, and too catastrophic. A single suit puncture, a power system failure during a dust storm, a medical emergency requiring surgery, a propellant production shortfall, any one of these events occurring in isolation might be survivable. Occurring in combination, which is what probability theory tells us we should expect over the course of a 2 to 3 year mission on an alien planet, they are not. There are scientists who argue that these challenges are solvable given sufficient funding and time. Some point to nuclear propulsion, which could reduce transit time to around 3 months and dramatically lower the radiation exposure window. Others point to advances in artificial gravity through rotating spacecraft sections, which could mitigate bone and muscle loss. Some suggest pharmaceutical interventions that could slow bone resorption or advanced radiation shielding materials. These are not unreasonable positions. Science has a long history of solving problems that seemed intractable. But there is a difference between difficulty and impossibility, and that line is drawn by physics. The radiation environment of interplanetary space is not a technological problem. It is a consequence of the laws governing how charged particles interact with matter. The tyranny of the rocket equation is not an engineering shortcoming. It is Newtonian mechanics applied to the mass of the cosmos. The biology of the human body under sustained microgravity is not a design flaw that better engineering can fix. It is the result of 3.5 billion years of evolution on a specific gravitational surface. You cannot simply update the firmware. The universe does not care about our timelines or our ambitions. It operates according to principles that were established at the moment the cosmos came into being. Principles that govern the behavior of every atom in your body and every photon crossing the void between worlds. When we look at Mars through the lens of those principles, what we see is not a destination waiting to be reached. We see a planet that the physics of biology and rocketry and radiation has placed, for all practical purposes, beyond the reach of human beings as we currently exist. That is not a counsel of despair. It is an invitation to ask a deeper question. Not how do we send humans to Mars, but what would it mean to genuinely remake the biological systems that make the journey so dangerous, and whether what emerges from that remaking would still be, in any meaningful sense, human. The universe is under no obligation to make its wonders accessible to us. But in the gap